All right, so today we'll talk primarily about the midterm. I'll try to get do a quick review of everything we've covered. It's shocking that we're already sort of halfway through the semester. But I was looking at all the stuff we've talked about, and it's also a surprisingly large amount of stuff, so that's good. Before that, I think we had, before I forget, for the midterm, it'll be a closed book. We don't have a book, no PDFs, but you're allowed a sheet of notes. So one letter-sized sheet of notes could be handy. Some people find it instructive just to make the sheet, so why not? Okay, so we were talking about Openmp last time, and there was one little thing I wanted to finish up with there. In fact, maybe just write down a few things here. So there's the, all of these are like pragma, omp, right, and then something. So parallel just makes it go run a whole bunch of different threads doing the same thing, right? And then within there were a few other options. So we could say single, and then we'll run inside of a omp parallel. Now this part is only running as on a single thread. It's really handy for some sort of initialization and that sort of thing. And then there was a for, which splits the for loop over all of the threads that are running in this parallel section. Lots of attributes where you can specify like how many threads you want to run this parallel section and such, but we can ignore that. This is the main construct for data parallel programming would be this for loop, basically, split out. And then there were a few interesting pieces. Perhaps the barrier is quite useful, right, to make everyone wait. There's an alternative to single, which is called master, which is only run by the master thread. And then there's the critical. So a critical is like whatever's left of the block or whatever's inside of a following block is a critical section. So it'll be run by all the threads, but one at a time. I think those are the most important parts that we discussed. And there's one more, which is new to Openmp 3, which is pretty cool. It's called task. So basically all of Openmp relies on this general idea of having a bunch of worker threads that you start up initially, and they have some sort of virtual queue of jobs that they need to perform. So in the sense, in the case of a for, you would the compiler, one way or another, splits up the for loop into a bunch of different chunks and then schedules those chunks or puts those chunks into these queues for the various worker threads. So if you were to schedule, in fact, maybe I think we had an example here. Let's see, test.c. So in this case, we were saying, this scheduled, let's see, the guided is maybe a little too advanced, but basically if we schedule with static and you say 1, that means split this for loop into 1,000 different tasks. Every chunk of this for loop being size 1, you get 1,000 different tasks. And then distribute all these tasks into the queues of the various worker threads. It's not clear that you would have an actual queue sitting there, right? But at least there's a sort of first in, first out idea for each one of these threads. Okay, so underlying this for loop primitive, there's a concept of a task that is, in this case, a small chunk of the for loop that is performed by the various threads. Now the scheduling can decide. If you do static, then you have a sort of round-robin scheduling, right? If it's dynamic, you could think of it as one shared queue and all of the threads pulling from the same queue. And then this guided is is like a dynamic where you have a shared queue, but you have smaller, let's see, big jobs initially, like big tasks. Maybe you chop up the for loop into, say we have 10 threads, you might do chunks of 50 initially. So now you got the first, everyone has done 50 each, now 500, half the loop is done in one chunk. Right? But then maybe you go 25 or 10 for the next, so smaller and smaller pieces. This is to achieve balance because some chunks might take a longer time to run. This example that we were running, which was a crap example, because the sleep was way longer than I kind of figured out in my head. But if the tasks are of various length, then you really want to have as fine granularity as possible, like make all the tasks really small so that all the threads have something to do at all times. So this guided here it's not very guided, it's just that it starts with big chunks and then makes smaller and smaller chunks, and toward the end of the for loop it's maybe just the one. Okay, but this, actually, maybe one more thing. So with this omp parallel, basically you make a task out of the entire block that's below it, right? The entire parallel block. You make, if you have n threads, you make n tasks and queue this in every queue, in the queue of each of the threads. So they all end up running the same task. So what was introduced in Openmp 3, and I think that was the only really big difference, was the idea that you can also explicitly schedule a task. The user, the programmer, gets to directly make a new task start. So maybe we'll give that a shot. Let's see. Oh. Where's all this? Test.c. Oh, looks like it's not mounted anymore. Yeah. Okay, so here we're letting Openmp do all the scheduling for us, right? Splitting up the for loop and so on. But we don't have to go like that. We could say pragma omp single instead. So now this is all running in a single thread, but then we can say, okay, why don't we have each round in this for loop be its own task. Oh, that's weird. Like that. I guess Emacs isn't all that happy with all these pragmas. It looks a little awkward. Okay, and so now this will be its own task that's run in parallel. So let's see what happens if we just print something out. Okay, so I think that was it. May have to look up the documentation. Oh, present I. Yeah. Great. That'll be better. Okay, so what's going on is this omp parallel starts all these threads, but then we say, oh no, by the way, let's just run it on a single thread. But then we're creating all these tasks, dynamically creating a whole bunch of tasks that end up in some run queue, wherever, whichever thread has nothing to do will get to run these various tasks, and then they should all have their own copy. So this is nice here. See this I, the I keeps changing, right? But when you create a task, you get a copy of the I. So all of these little tasks will have their own private copy of I, so they should all print out different values. Let's see what happens. Yeah. OK. So this looks relatively reasonable, but you'll notice it's not all in order. Right? So that's because these tasks are running on different CPUs, depending on which CPU is ready to go. In fact, why don't we try one more thing? That's probably better than last time. OK. Right, so this is 64 threads printing something out every time, I think. Oh, oh yeah, so now they're all different lengths, right? Because different sleep lengths. But at least we see there's a whole bunch of things going on in parallel. OK, so when would you want to use these tasks instead of a for loop? Imagine you're traversing a binary tree. So we actually want to, we want to sort of visit all the nodes in the tree as opposed to just finding the minimum. Or, yeah, that's good. So I guess that's one option. So we want to just visit all of the leaves in the tree. So now you could say, let's see, we go like this. One task that says visit child 0, right? And then you make another task that visits child 1. So now suddenly you have 2 threads running on 2 different CPUs, visiting 2 different children of the thread. And now they do the same thing recursively. So now we have 4 threads running at the same time, and so on. So you might end up with very many of these tasks kind of multiplying, and then the scheduler will at some point just figure out which order to run them all in. There's a bit of a weakness here, and let's try that too. With print, it probably doesn't matter, but let's say we want to do something like this. Oh, this is actually, let's see, what's a good way to do this? Don't have a good demonstration, but basically, OK, so let's not run it, but so here, we're running this loop a billion times or so, and we're creating a new task for all of them. So now you could imagine this queue. Right? If we were to run this, keep running this loop, you'd have a queue of a billion elements. It'll take forever just to make the queue. It'll take much longer than computing the sum itself. So probably you don't want to use such fine-grained tasks, but also the main thread that's running here that keeps creating these tasks, it's not going to get scheduled forever. So the runtime will detect that oh, the queues are way too long. Let's use this thread that's currently executing the creation of tasks. Let's just use that one to try to empty the queues a little bit too. So it does some relatively clever scheduling there. Of course, with all of this stuff, right, there's overhead. It takes work for Openmp to know what's going on, and then that's work that we could have used to do something better. So if we know exactly what we want to do, probably we're better off writing a pthreads application directly if we're in a real hurry. Okay, if the program needs to run really fast. But if we're in a real hurry to write a program, maybe Openmp is the better way, because it's really little code to achieve a lot of concurrency in the program. So I guess it's a nice tool to have in your toolbox. I would hate to be an Openmp programmer full time, just because it's not really a language. It's messy. Like I don't know, a task should be a type. It shouldn't be like this thing. So if you want something prettier, probably want to go with Rust. There's some maturing Actually, Ben, what's it called? The Openmp equivalent for Rust. What's that? Crossbeam could be it. That's not the one I had in mind. There's Rayon. That's the one. Yeah. I'm still kind of hoping that at some point we'll switch our curriculum over to Rust. It seems like a good choice, but actually, let's do a quick survey. Who would prefer that all of the UIC systems classes were taught in Rust rather than C? Well, you basically have to make that choice because it's an enormous learning curve for, say, half a class. If I was to do this class half Rust, half C, no one would learn Rust unless we did the whole thing, and then we'd spend a lot of time learning Rust. And so it should be taught in 361 so that you have it when you go to the other classes, and then basically now you don't have C anymore. All right, so we only have 3 wanting Rust rather than, okay.
I've never seen it, so I don't know.
Okay, so maybe spend a few minutes on it. So Rust is a systems programming language, just like C, meaning you write some code and you pretty much know what it generates. You know what assembly is going to come out. There's no runtime. There's just, sometimes there's some helper functions being called, but basically it generates sensible assembly. That's that. There's no garbage collector, and so on. Okay, so the language is a relatively modern language. It's strongly typed. It's called a linear typing language, where basically it prohibits race conditions. So you cannot have 2 threads that access the same, have access to the same variable unless it's a read-only variable. It just can't be expressed in Rust. And so that means the compiler is going to give you a lot of trouble because you're used to accessing global variables, plussing whatever you want. But unfortunately, it would have to be either read-only or you have to have a lock around it, or you won't be able to access your immutable variable like that. So lots of stuff like that. So it's a kind of a pain in the ass, but it's hard to write a buggy program, at least a buggy concurrent program in Rust. So the hope is that in the future, this will be the language that everyone uses for systems work. This or some other language, but C really is very close to assembly. There's no safety whatsoever in there. And it's really outdated in the sense you can't pass, say, a sized array as an argument to a function in C. What is that? Like, I would like my function to take an array of size 10, right? Of an arbitrary type, ideally, right? But there's no way to describe that at all in C, and it's kind of ridiculous at this point. There should be a way, and Rust allows that, and lots of other things. But it comes with the drawback that it is quite a learning curve in order to get something to work. In C, you can get something to work really quickly, but usually it's a buggy program. And in Rust, it takes quite a while to get anything to compile, and then usually it's right by the time it's compiles, right? Yeah.
And to be fair, once you get used to working with the rules of the system, and you understand them, you don't make mistakes as often, and it takes far less time to actually get something working.
Working correctly, right? Yeah. But I would probably argue that to do a quick and dirty thing, C is still faster.
Obviously.
Right? It's just some extra work in declaring what these variables should be behaving like. Right? Yeah.
Do you think it's actually going to reach large-scale adoption, or is it still too immature? It just needs more time?
I mean, so it's still evolving, which is unfortunate for a systems language. You would want it to be stable so you can build things long-term for it. It seems like it's stabilizing. It's not a very popular language now, and C has an enormous legacy. Like it's 54 years, I think, of code, right? And so times however many we're working on. So it's a little hard to replace it, but it's the the momentum seems to be there. So maybe these things can change very quickly once they start changing. It's an exponential curve. Yeah.
Firefox is right now shipping with a piece of its styling engine, which is written in Rust, and then building a full rendering engine in it. That's the whole reason why it started in Mozilla.
Right. Yeah, they figured it's difficult to actually get Firefox to not crash, and so they need a new language where you can't have such crashes, and that seems to have worked out somewhat. But they're still struggling with actually like building the whole thing. So Firefox is a big machine, a big piece of software, and porting that is not easy. So it's a challenge there, but I think that there's lots and lots of opportunity, and it might be time to move on from C, because it's like, how long are we gonna stay with this dinosaur? Right? It's an awesome dinosaur, but yeah.
I don't know if you've come across this in anyone you've taught, but do you feel like people who learn the Rust approach of like ownership and borrowing write better C, or does it not transfer over to writing C?
Oh, I have no idea. I think that whoever learns Rust now has a particular interest. Right? They probably understand what concurrency is, and you do Rust because you want to write concurrent programs, and so it's going to be all biased anyway. But I would imagine that if you are used to writing Rust code, you would hate to go to C, and you wouldn't do it because the compiler is so incompetent. But I don't have much experience with it myself. I'd be excited to switch to it though. So we'll see. There was one good argument I just read today. Intel, they released their new i7 chip. I don't know if you heard. But basically it's a failure in the sense that since 2014, they haven't been able to shrink their transistors anymore. They're still at the 14 nanometer node, as they call it. And so Moore's law has more or less stopped. Maybe it'll grow a little bit. So for a while, Moore's law, people were thinking about it both in terms of clock frequency and chip size, right? Or number of transistors. And yeah, Moore, he only really talked about the number of transistors, but the clock frequency was also going up exponentially, and so that was great. And then that stopped, early 2000s maybe, and then now it seems like the shrinking has also stopped. And so two things will be happening. Probably one is you'll see larger dies. Like the cost will still probably keep going down for if you keep having the same process. So you'll see larger and larger dies with more and more cores on it. And then at some point they can only get so big, and maybe you have to write smarter programs. Hopefully we won't get there just yet, because writing smart programs is really hard. But anyway, you will be seeing larger dice, which means more cores, which means everything's going to get much more concurrent. There's no getting away from it. So single-threaded programming is not something we can rely on. And multi-threaded programming in C, as we have found out, it's a pain in the ass. And so probably we have to live with Rust in the end. That said, I think many employers still want to see lots of C experience because they have millions of lines of legacy C code that needs maintaining. So.
To be fair, there are jobs coming up for Rust programmers as well.
Yeah, fine. Yeah. So you'll see 100,000 jobs for C and then 100 jobs for Rust. But those 100 Rust jobs will be so much nicer. Right?
Yeah.
So
For a startup, right?
yeah, I think it's like that. 'Cause who wants to maintain all this legacy code? C will be the COBOL of the future at some point. It isn't yet, but maybe Rust will make it. So we'll see.
They said that 20 years ago, though, too, right? The C was going to fade out.
Yeah, but it has for anything except systems programming, right? You don't write. Like even if you want your program to run fast, you don't really run it in C anymore. Like it's unusual. But you can't write an operating system in anything except C, except for Rust, because there aren't any other good alternatives to C. I mean, I exaggerate. There are some others, but they're all minor, and Rust really has a lot going for it in that regard.
D one of them?
What's that?
There's D as well.
Yeah, D is one of them. But it doesn't have anything near what Rust has to offer. So. Okay, anyway, we should talk a little bit about the midterm. Certainly sounds like we should be sticking with C for at least another year, and then we'll see. I'll ask again next year, when we have a majority wanting Rust, and we'll try to switch it. Okay, right, midterm. So the midterm will be comprehensive for everything that we've talked about except Openmp. So I thought we'll go through what we actually talked about, not all the details, but if you have questions along the way, that'd be great. And I've added some references to the textbook, or to the textbook. I will try to flesh out the actual writing a little further, but don't rely on it. So if there are topics in here that you feel, oh, I actually don't know how that works at all, try to figure it out. Find a way, ask questions on Piazza, find some documentations, ask me, come to office hours, so on. Office hours are actually, I don't have any more office hours before the midterm, so that's not going to work. Okay, so what have we been talking about? I think the first step is to make sure you are familiar with the units and the sort of typical quantities. All right, so units and prefixes, like what is a cache line? All right, bytes and bits and kilobytes and all that. Make sure you get it. And then typical quantities. I've been throwing around numbers quite a bit throughout the semester. So some of the things that you certainly want to know about, cache line size is 64 bytes, right? If you think it's 64 bits, everything is going to get really weird. And then a word, like what we usually operate with, is 64 bits. That's because it's a 64-bit architecture. There's also other quantities. Right? So like how long will it take if you have an L3 or LLC miss? Like accessing memory from DRAM. It's a good idea to have a sort of order of magnitude estimate of these things. And so I would say probably it'll take you some 200 cycles, something like that. I might be off by a factor of 2, but probably not more than that. And then how long will it take you for the other cache levels? So I think an LLC hit is probably about 40, an L2 hit is about 10 cycles, and an L1 hit is about 4 cycles. Why should we remember all these constants, right? They're just constants. Constants can change. Well, it's not really like that. The actual constants will change, but the relationships between them probably won't. And so we need to have a rough idea of what's going on. If you think it's going to take a microsecond to read something from your L1 cache, you're just going to be off by a factor of 1,000 on everything you're doing, and that's no good. So that's why we need to know some of the constants. Okay, so let's move on. We need to know some of the profiling tools. So these are examples, right? Dig around, try to get as many of these quantities as you can into your head, or at least onto your little sheet. Head is much better, because then you can think about these things rather than look them up. And when something is really wrong, it's obvious that it's really wrong, as opposed to I have to do this calculation and then it turns out that, yeah, that wasn't right. Okay, profiling tools. Definitely want to be familiar with perf, stat, and record, and report. And there's the other one, annotate, which we haven't used explicitly, but that's basically what happens when you go all the way into a perf report. and hit the annotate thing in the menu, then it comes up the assembly layout with all of the percentages on it. That's perf annotate. So we want to be familiar both with sort of what these things do, but also their weaknesses, right? What they don't do, and how they work. Like how does perf stat know how many cache misses happen during the execution of this program? That's a hardware performance counter. It's sitting in the chip. Perf stat can read the performance counter before the program starts and after the program ends, and there it is, pretty much. The OS has to help a little bit because you might have switched programs during the execution, and so this program isn't responsible for all of those cache misses. But anyway, and then how does perf record know what you were doing? Bunch of interrupts, right? We're sampling regularly and so on. Okay, so knowing how these things work is good. You also want to know about get time of day, which is probably based on RDTSC. It's an instruction read timestamp counter. RDTSC says how many cycles have passed since some arbitrary time. So you just read it over and over, you know how long things are taking. You want to know about the impact of these tools and of I/O. So impact of measuring on actual execution. So if you have a multi-threaded program, these measurements might reorder the actual execution of the program that you're trying to measure. If you have a bug you're trying to track down, sometimes the bug disappears. If you put some extra instructions in there, that's called a Heisen bug. Bug that is only there if you're not looking for it. And certainly if you're trying to printf something, you'll see a dramatic slowdown if you print too often, and so on. Okay. So we want to know, oh yeah, time is a useful program too. Very useful. And the output, you want to understand the differences between this real time, the user time, is it called system or kernel time? Okay, then we have a single-threaded performance. So we want to have an idea of how, implementation of C in assembly. Right? Not how we write a compiler, but what is it that a function call actually does? If you need to be familiar with stack frames and local variable being in a register or in a stack frame in order to reason about some of these questions. This is more of a 361 topic, but certainly want to brush up on that if you don't have it already. You want to know the differences between like stack, heap, what is a local variable, how do these parameters pass between functions, right? Global variables. So these are sort of implementation details of the language C. Right? It's not obvious that every language would have a stack, right? But C does, and that's the one we work with. Okay, probably have some idea of malloc as well. That's the heap, by the way. Like anything you malloc, that's basically your heap in C. Okay, we want to have an idea of instruction throughput versus latency. Right. So looking at this Agner-Fogg kind of instruction tables, or I think it's listed here and there by Intel too. Like an instruction you might be able to run, say, a multiplication instruction every cycle. But if you need the result of the multiplication, it might take 15 cycles before you actually can use it. So that's the difference between throughput and latency. You probably want to have some rough idea of basic instruction costs, let's say. So, adding two register values to each other, how long is that going to take? Depends a little bit, but it probably one cycle will be the latency. You probably can run 2 or 4 of those in one cycle. It's relatively easy with these with instructions that just use register parameters, because that's well known. You don't need to know all of them. Just have a kind of an idea. We're talking about one cycle. We're talking about 100 cycles. What's going on? Whereas if you're accessing memory, then it all depends on the actual memory access, which varies depending on the state of the memory hierarchy or cache hierarchy, and we'll get to that in a moment. You want to understand this data dependencies. Let's see. Let's talk about out of order execution first. Out of order execution, which has like this reorder window. Right, so some window of instructions is executed in arbitrary order, subject to some constraints. There's data dependencies, which you can't get away from. So if you need the result of a previous instruction to execute the next one, well, you're not going to run the next one until you get that result. And subject to some order constraints based on the Intel memory consistency model. They don't really call it a memory consistency model. It's not a formal model, but there are some guarantees here, right? Stores happen all in order, for example. Okay. Might be useful to be familiar with the instruction reorder window and the register renaming buffer, just to kind of know how these things fit together. And then the store buffer. Yeah. Okay. Oh, and execution units. Right. So how do these things all fit together? You have first you're parsing some instructions to create micro-ops and whatnot. That's sort of the front end. And then you have your out-of-order execution window, which is all the things that we want to run at the moment. It's a fixed size, so it can't go any further down until you've finished the instruction at the top. Instructions within it are executed out of order, subject to all these constraints. And then if you don't have enough instructions to run, you might end up doing speculative execution. So let's say we have finished all of our, everything in the window is finished, but there's an if condition. We say if x equals 5, but we just don't have x yet. And then there's all this stuff inside of if x equals 5. So now the execution window has basically one instruction in it, one that we can run. That's we're waiting to do that comparison between them, and then there's a branch. So, okay, call them 2 instructions, both pending this read. Speculative execution says, okay, fine, I don't know what else to do, so I'm going to assume that it'll be yes, it's a 5. In which case, I can run all these other instructions inside of the if condition. We'll try that. Using the store buffer, we'll kind of hold on to the stores to make sure we're not causing any weird effects, any observable effects for anyone else. We'll just hold on to any store to main memory until we see that, oh yeah, x was equal to 5, in which case we can actually release all those stores. Otherwise, we'll have to roll back and invalidate all the work we did in between. But that's speculative execution. Just because I remember it now, missed speculation costs 20 cycles. I don't know if you need to know that, but it's good to have sort of an order of magnitude idea of what's going on. So of course you lose all those instructions that you ran naturally. but then you also lose another 20 cycles of just kind of the cost of rolling back to where you were. Not bad. And if you guess right, then you could win hundreds and hundreds. So it's good. Okay, that's speculative. And then we need to know understanding memory access. That's a complicated topic. So in a just in single-threaded, we'll start with that. We need to know the difference between registers. And I already put that maybe. Oh yeah. Well, I put registers here too. Definitely don't want to be confusing registers with stack with global variables and so on. Okay, so memory access. What does a load do? Like, how does a load actually work? In some detail. So we're trying to load a certain memory address, right? The contents stored at that memory address. And now, what happens next? First, we have to see, did we store to that memory address recently? Because if so, the value is sitting in our store buffer. It's the first step. And then, if it's not in there, then we check our L1 and our L2 and our L3. And if it's not anywhere there, then we go and load it from DRAM, unless it's a multi-socket machine, in which case we also have to see if anyone else has it. And how that's coordinated, we don't need to worry about. Okay, and then how does a store work? Well, sort of the same idea, except so now we need to get the appropriate cache line into our cache, and then make sure that we're the only ones that have that cache line, because otherwise we could get inconsistent results. And then we write it to the cache line. Of course, that's going to take forever, so it doesn't actually work that way. Instead, what we wanted to do is add it to the store buffer, and we do that in parallel, and now we go and run something else at the same time. So the store buffer will only release that store into the cache line or into like visible memory after the cache line has appeared in exclusive mode in the L1 cache. Okay, same thing for store. All right. So of course there's many more details, but we're looking at sort of high-level effects here that could affect performance. Okay, some more things about the cache. So the cache line granularity. Right, any access to memory, generally speaking, will end up being 64-byte granularity. If you load 1 byte, you actually move in 64 bytes into your cache. There's the associativity, which can be extremely performance sensitive especially if you have these regular size arrays and there's some multiple of the cache line of the cache size or some even fraction of the cache size too. And something about alignment. Oh. So you probably want your values to fall only on one cache line if you can choose to do so. And so sort of what does this alignment mean in terms of the actual address? Right? It's probably a bunch of zeros at the low end of the address. Okay. Actually, before I move on, questions. These things can get really tedious, so it's better if we have questions, talk about something else. Yeah?
Does the speculative execution always get the same outcome?
No. So there's different branch predictors in different CPUs, but one common way is to have a little cache that says, oh, this instruction, like this value of my program counter, last time it was a yes. Or maybe like some statistics for a bunch of instructions. And then of course there's a limit to how many you will have, so maybe you have like 100 slots or something. And then at least if you're doing a tight loop, it'll be enough with just a few slots. So you could imagine in a for loop, it's a long for loop, the branch, the for condition, you really want to get that one right. So that will be after one time around the loop, very simple predictor would guess right all the way until you get to the last entry. That's beautiful. I think that's probably the dominant effect of the branch predictor. If conditions are, they only happen every now and then, but a for loop, that's a lot of branches. Let's see. You can also provide a hint. You may have seen this, if you're looking at the Linux source code at some point, you may have seen sometimes inside an if condition, it says like likely, and then the condition. Say if, and then likely, and the condition. And that translates into a hint that goes before the branch in the assembly. So the CPU knows, like, oh, here comes a branch, and it's probably going to be true. And so then it can do a better job of predicting that one. You don't see it very much. I think it's probably because the predictors have gotten good enough that it's not worth the trouble, but I could be wrong. I've only ever seen it in kernel code too, but I don't think that has anything to do with it. Could be you can only use that in supervisor mode. Other questions? Okay. So that was memory access. Right, the memory hierarchy. Probably a good idea to know about so cache misses and hits, and also page faults. Right. So page faults aren't really a topic for this class. That's a 361 topic, but still a very good idea to at least know the difference between a cache miss and a page fault and a seg fault, let's say. Actually, can anyone tell me the difference between or the relationship between a page fault and a seg fault?
The OS determines it's illegal for a seg fault, or maybe more access.
Exactly, yeah. So a seg fault is, I think, always a page fault. It starts with a page fault, which is just an interrupt to the OS, and then the OS decides whether or not this was a good one. A good one would be you're trying to access some memory that wasn't yet paged in because the OS had paged it out to disk, or because it had lazily allocated this memory, or whatever. And then it just fixes the problem and returns to the process. A seg fault means the process did something it wasn't supposed to, and then it kills the process instead. Okay. We also want to have some idea of compiler. So we don't need to know how it does what it does. That's forget the number, 467 maybe, the compiler class?
773.
Is it 473? Ah, okay. But we do need to know some things like what it does, not how it does it. So certainly want to know about reordering of instructions. Oh. And dead code elimination, inlining, common sub-expression elimination. Basically, the compiler being clever. So if you have a for loop and you're doing something inside of the for loop that always yields the same result, the compiler will do that outside the for loop, generally speaking. The optimizer will move it outside. Loop unrolling. Am I missing any really major optimization here that you can think of?
Moving values into registers.
Oh yeah, there's no choice but to do that. But that's good. So I don't know what you want to call that, but I don't know what I want to call this. Maybe like eliminating some loads is probably what it is. But if you want to actually run any sort of instruction on a value, it has to first be in a register. But yeah, it's not storing it back to the stack all the time. That's a good one. Well, yeah, so the compiler will take your code and it will try to create a piece of assembly that does what you meant, not what you said. Right?
What do you mean by dead code elimination?
Dead code, yeah, dead code is code that either doesn't get run or doesn't do anything useful. Maybe I'm using the wrong term. Certainly code that doesn't run is dead code. It sounds a little weird for the other one, but I don't know what a better term is. So if we're calling, we had an example last time, I think, if you're calling a pure function over and over, you're not using the results, you could just eliminate the call to the pure function, because a pure function doesn't have any side effects, so there's no cost to just removing it. Yeah.
What about const expressions and const functions and all those things?
Const functions are a C++ thing, and I think that is with respect to a particular object, that it doesn't change the object, but it can use values inside the object. In our case, in C, there's no C standard for functions, but you can use these attributes, attribute const or attribute pure. Pure means it only uses the inputs.
No side effects.
No side effects, and it doesn't load any global variables. You could imagine a function that doesn't have any side effects still depending on some other context, like some global variables or something else. So that's a const, attribute const, but an attribute pure means it's only the inputs. I suppose that enables some extra optimizations. Okay, so the point of all this, well, of course, the compiler does it to go faster, but we need to understand it so that we can read some assembly and have an idea of what happened. Like, how did the code end up like this? And maybe sometimes it's more like, why didn't it apply this optimization? Right? So why did it not inline this function? It's such a small function, I keep calling it. Well, it couldn't inline it because it wasn't in the same object file. It didn't even know what the function was. That sort of thing is good to know. Or why does it keep reloading this value from a global variable? Why doesn't it just keep it in the register? Well, it is specified as a volatile, so you have to reload it. So maybe a good idea would be to say, take a copy of the global variable to a local variable if you know you want to operate on the same value over and over. Things like that can really help the compiler. And knowing what the compiler does is important so that you can tell when it made a mistake. It doesn't make mistakes, but it doesn't do what you meant because you didn't say it properly, right? So it kind of misunderstood you, I guess. So I think it would be cool to have a question on the exam that says, like, oh, here's some assembly. What did I do wrong? Like, why did it do this? And so then we have to fix the C code. Right? That might be a cool question. I've written some of the questions, but it's not done yet. So. Right, instruction reordering, the compiler sometimes will reorder code. It's not that it reorders code like, oh, it would be better to do like reading the variable before you do that store. That's really not something that it would do, but it would take an instruction outside of a loop, like from inside the loop, and put it outside the loop. And that still reorders things. So it'll be confusing that, oh, I told it to read it inside the loop, compiler puts it somewhere else. That's reordering. If you want to avoid that, you have to put in a compiler fence, right? And that was this thing. I don't know why it has to be like this and doesn't have a shorter expression, but this is a good way. okay, so that prevents the compiler from moving instructions before it. So if you have this inside a for loop, nothing inside the for loop can go to outside the for loop. Of course, your for loop is going to be a lot slower too. It's always the cost of preventing reordering. Right, some important keywords. Volatile, const, restrict, which is pretty cool. Just recently discovered myself. What else? Static. Yeah.
Question about the memory, the SM volatile. So you said if we put it in a for loop, it does not reorder it for the for loop. So does it also prevent the speculative?
No. So this doesn't produce any assembly. This only produces, like, tells the C compiler to not do certain things. If you want to prevent the machine from doing things once the assembly is produced, you have to use an mfence. We'll get that to that in a little moment here. Okay, so then we get to multi-threaded consistency. All right, so you will want to know something about the operation and effects of the cache and store buffer in regard to this. So basically, the main thing is what Intel says reads can move to before earlier writes. Right? That's really, in the end, that's sort of the observed effect of it. You can get some stale values. Your cache might not have been validated yet. You're reading some old values. Maybe that was because whoever did a write to this value, the write is still sitting in their store buffer. So generally speaking, values that you read tend to be stale, unless you specifically say, I need a fresh value. Okay, so if you really want a fresh value, what can you do? You can use atomic operations, right? So then we're guaranteed that whatever the read that was part of the atomic operation, if you're doing a compare and exchange or an atomic increment, we're reading the actual current value, then deciding what to do, and immediately operating upon the value. So that could be incrementing it or replacing it with something else. So atomic operations, of course, are slow because they do require lots of coordination between the cores. The beauty of all this asynchrony with stale values for reads is that you don't need to really coordinate with the others. You just kind of take the values as they show up and you'll be fine. But sometimes we can't afford that for consistency reasons. So sort of, yeah, and impacts of these, right? Let's see. No, actually, let's go like this. We say, okay, you definitely need to know about allowable reordering of instructions. So I would take a look at the Intel manual. I think it was section 8.6 where they talk about these reorderings. That's what we had up on the screen before a couple of lectures ago. The main principles being all stores are always observed in the order that they are in the code. Not in the C code, mind you, but in the assembly. Right? The compiler can still decide to reorder them in C unless you tell the compiler not to. So that's the main one. Stores are in order. Also, loads are in order. And stores can't advance in front of, let's see, no, stores can't go before earlier loads, right? But loads can go before earlier stores. So basically, you get, you can read stale values is sort of the principle. But I think trying to wrap your head around these properly is a good idea. Okay, if you want to affect, like if you want to operate beyond the standard sort of reordering constraints, you have to either use atomic operations, which are perfectly ordered, or you can use an mfence. In some cases, mfence will prevent reordering within one chip, but it has nothing to do with the other chips. Right? Atomic coordinates with all the other chips. And mfence just says, finish all your stores. All the stores that were before the mfence, they have to all finish up before you start any loads after. I think that's the main effect. Of course, it will also not allow any stores after the mfence to move to before the mfence, but they're not allowed anyway. Same thing with the loads. I think the main effect is basically drain the store buffer before issuing any further load instructions. Right. There's also the L fence and the S fence. L fence orders only loads, S fence orders only stores, but they're already ordered. So unless you're using streaming stores and loads, which we haven't really talked about, those are unordered. I don't think L fence and S fence have any effect worth mentioning. I could be wrong. If anyone knows differently, please speak up. Okay. Right, synchronization. Again, these are sort of more introductory topics, but you certainly want to know something about locks and condition variables and barriers and join. Fork join. Right, and what you could expect there. So basically, locks and condition variables and barriers, they do not permit any reordering between like across those operations. So if you have a barrier, you can't go and load a value before the barrier, and the compiler enforces this because it doesn't reorder beyond function calls, I think. I could be wrong. I don't know actually how the compiler gets it right. That's probably it. And then the processor enforces it because all of these operations are based on atomic operations, and you don't get to reorder instructions across atomic operations anyway. It would be really hard to implement synchronization operation without atomic operations because of that. Because the CPU would then reorder instructions across them, and that would really be weird. Okay, and then there's multi-threaded performance. So we want to understand false sharing, true sharing, of course. False sharing being two variables that happen to live on the same cache line. And so now it sort of performance-wise, it looks like it goes as fast as if you were accessing the same variable. But you still get correct results. With true sharing, it's a little more dangerous. Now it's going to be slow, just as slow as with false sharing, but then if you're not using synchronization, you would also end up with the wrong value because of race conditions. Yeah, maybe I should clarify that the store buffer holds the actual stores. It doesn't say like, oh, I'm going to use this value for the whole cache line. It's not the 64-byte value we're putting in. If we do a move of 1 byte, it's the 1 byte move that's in the store buffer, and that gets applied to the most recent value of the cache line. So if you have two variables that are sitting in the cache line and you want to write to the second variable, the first one is unaffected. Right? If it wasn't like that, things would really be difficult. Okay, so definitely want to understand the impacts of false sharing, the impacts of atomic operations, like how. So they run slow, but why do they run slow? There's a couple reasons. One is that there's just some overhead in the coordination itself, but also it prohibits reordering. Right? So your otherwise single-threaded operation doesn't get to run out of order because you had an atomic operation in between. The sort of the performance impacts and impact of shared memory access. So basically, what's going on with these cache lines, right? You have two threads reading from the same variable. Is that going to be slower than one thread reading from it? Doesn't make a difference because it's shared. But if you start writing to it, suddenly it's much slower because only one of them at a time can write to it. But then also the effect of out-of-order execution and store buffer on this. So yeah, maybe it is a lot slower to write to this shared variable, but you don't always see it because we have all this other stuff we can run in parallel. So maybe it's fine. And in particular with the store buffer, you have a whole bunch of stores queued up. You don't care that it's going that those are happening a little later as long as you still have room in your store buffer. Unless you have an mfence in there, in which case nothing will run until you've drained your store buffer. Right? So it's a lot going on in this machine. Trying to get a grasp on the various pieces moving together would be a good idea. Yeah, so I think that pretty much wraps up the midterm topics. More questions? Yeah.
You mentioned one type of question earlier. Are there other specific types of question?
Okay, let me see. I mean, I'm not saying that would show up in the midterm, and it all depends on if I can come up with a good question to ask, right? But some other ones might be, oh, here's some perf output. Why is that instruction so slow? Right? Here's an assembly program. It produces the wrong output. Fix it. Right? So it's a concurrent program. There's a race condition. Fix the race condition, or identify why there's a problem. Here's a C program. It runs really slow. Right? But there's no perf output this case. Maybe there's perf output, maybe not. But like, either why is it slow, or how would you fix it? Maybe you can't fix it, but it depends. It won't be questions like, oh, explain how the store buffer works. Right? That's not it. But why does here's two programs, one with an mfence and one without an mfence. You might want to point out that the mfence requires draining the store buffer. Perhaps that might be nice. Yeah.
Do we have an idea of how many questions there might be in the exam?
That depends on how you count questions. So usually a question will have several parts and things. Probably be, I can't answer that one. Yeah. I'll try to put it this way. In almost all my exams, people finish before, but they don't necessarily know the answers. Right? It's not that you run out of time. It's just like, I don't know. I'm gonna try to make it less I don't know, but it doesn't. Yeah, it doesn't tend to be that time is the main constraint.
Oh, I hate to ask this question, but some teachers they'll say you can have one sheet, but don't specify what they mean by one sheet. Does that include front, back, like?
Oh, yeah, fine.
Okay.
Put whatever you want on the sheet. Micro type, bring a.
Okay.
Yeah.
Magnifying glass.
Magnifying glass. That's right. Yeah.
That's when I saw as a guy had a filter. He wrote them in 2 inks. Had a filter to see the other ink. That was a little much.
That's cool. It should be 8 bonus points for that sort of approach.
Really, really clever.
Yeah, I don't know that there's that much you can put on this sheet, but maybe, I mean, if you want to copy a page out of the textbook, that's fine too. We don't have a textbook, but you know, if we had one, bring whatever you want, but just not so much. Yeah. I don't tend to ask questions that are like, or recite all these numbers or like, anyway, so you have to have an understanding, and then there's be a problem question that you need to figure out. So textbook wouldn't help you that much. Yeah?
Is it mainly like short answer, or multiple choice, or long answer?
Short answer. Like, no essays. I hate grading essays. Multiple choice is awesome to grade, but they kind of suck. So, I don't know. Okay, I guess that's it. We'll finish a little early for once. I'll see you on Tuesday. Happy weekend.